Time.
Oh yeah. Yeah. But for that location, I'll send you a couple of pictures of the backyard. Because that, I mean, I don't know why I thought it was, I didn't think it was that far off. Great. There are some like for late lights in the house.
You're on. Actually, I gotta share the screen. Are we on? I'm sharing the screen. Okay.
There you go.
All right, folks, we're going to take your seats. We're going to get started.
And good evening, everyone, and welcome to the RASC Winnipeg Centre's monthly meeting. And welcome to everyone that's here at the University of Manitoba, as well as those that are online. I'll do our land acknowledgement. The lands from which our members and guests are joining us are located on the original lands of Anishinaabe, Cree, OJ Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So, again, welcome. I'm Dennis Lyons, and the host for tonight. So our sessions that we will be doing we have our beginner session shortly here with Scott Young. I'll be doing the welcome announcements, followed up by What's Up by Brian Stack, What's New by Jay Anderson, and then we'll take a short break. And then our main presentation by Gilles Ferrand will be on at that time. And what I'd like to do right now is welcome our beginner section speaker, Scott Young, who will talk about winter meteor showers. There's a tough word.
Makes sense. All right. So, winter meteor. Well, so first of all, we're here to talk about astronomy. For those of you that may remember, back in the old days, the sky would get clear and we could see the stars at night. And there's. Oh yeah, that's right. Somebody bought a new telescope, so it's been talking for a month. Great. Okay. And it's page up, page down, or arrows? Which is the button again? Page up, page down, or arrows?
It should be page down here. Yeah, there you go. These two.
Great.
Page good.
Okay. So I do hope to see skies like this again sometime soon. And this is a great time of the year. The problem is when it's clear now, it's cold. And a lot of people will say, oh, I don't want to be outside because it's cold. But cold weather is the best time to go stargazing. There's no mosquitoes. And you got beautiful clear skies. The skies are full of the brightest stars of any season. There's no mosquitoes. There's a lot of advantages here to observing in the winter. Here's the other reason. If you like meteors, falling stars, shooting stars, this is a plot of the rate of meteors throughout the whole year. January 1st on the left and December 31st about, right about here, I guess, and then that loops into the next year. This is, how many meteors per hour you would see plotted over time. And there's a peak there in the springtime. That's the Eta Aquariid meteor shower. A great one, but it's not bad. The Perseids happens in August. That's the one that everybody hears about. And because of the way social media works, it becomes a huge event and people go outside thinking there's going to be stars raining from the sky. And, they go out until like midnight or 1 a.m. and they don't see anything and then they get disappointed. The Perseids are only really good early in the morning. And even then, they don't always live up to expectations. Maybe it's because of those short summer nights that we have. There's a few other ones, but we're coming up to, we're right here today, and we're coming up to the ones that are labeled Gem and Qua. GEM stands for the Geminids. That is the best meteor shower of the year. Hands down, every year, it is always the best meteor shower. Even when the moon is going to interfere, like it will this year a bit, it's still a good meteor shower, and we'll see why. Oops, that's not what I wanted to do. The QUA stands for the Quadrantids, and that's the second best meteor shower in the year with an asterisk. That one, there's a few circumstances you have to sort of satisfy for it to really live up to expectations, but we'll get into that. So who has not seen a shooting star before? Anyone? Meteors, okay. They look like a star shooting across the sky. When you take a picture of them, it sort of freeze frames them like this, and we see the streak all at once, but often it's a small streak that is moving across the sky, and our eyes can actually see the motion of it. So it's a lot more dynamic than a picture like this can really convey. On any given night, you can see 2, 3, 5 an hour, depending on your sky conditions and so on. That's just standard, because basically each one of these things is a little piece of dust floating out there in space, maybe the size of a grain of sand, and it hits the Earth's atmosphere, or the Earth's atmosphere hits it, however you want to think about it. And as it comes through the atmosphere, the friction just heats it up so much that it vaporizes in a puff of light, and we see that from the ground all the way down here as a meteor. So that's happening all the time, because space is somewhat dusty. It's not really as empty as we often think. Just like the dust in your house, there are a few places where dust collects, though. So dust bunnies are like, I've got them under my couch or wherever the cat likes to sit, near the vents or whatever. In the solar system, those dust bunnies are left behind by these things. This is a comet imaged by Gia Walker back in just a little while ago. Something's talking. What is that? Is that the stupid telescope?
Smart telescope.
Yeah, no, I use that term on purpose. Yeah, it is just an impolite telescope. Yeah. A comet is a big snowball in space, and it loops around the sun in an oval orbit. And when it comes close to the sun, it starts to melt, and it grows that beautiful tail that we saw the image of, and that tail is made of dust. And as the comet goes along, that dust just sort of flows off the comet and then just stays in the path of the orbit. So this orbital path, the white orbit here, is basically a giant dust bunny all the way along there. And if that happens to intersect the orbit of the Earth, like it does in this case, this is comet 55P Temple-Tuttle, and the Earth's orbit goes through that comet's orbit around every August 11th and 12th, and it gives us the Perseid meteor shower. So every time the Earth goes through that spot, we go through a dust bunny and we get lots of shooting stars. This is sort of a side view of the same thing. Most of the time, these comets are not perfectly flat in the plane of the solar system. They're coming up from above or down from below, or they have very unusual kinds of paths. Most of the meteor showers over the course of the year come from comets like this. But the Geminids are different. This is a comet with all the dust and things getting blown off it in geysers and things like that. The Geminids, nobody knew where they came from. There was no comet in the orbital path of the Geminids, which has been seen for several hundred years already. So we know that something is making this dust bunny. Back in 1983, I think it is, or maybe 82, they discovered an asteroid that is in that same orbit, asteroid 3200 Phaethon. And so there was some thought, well, is an asteroid is that what's left after a comet goes around the sun so much that all the ice has melted and all that's left is rock? No, turns out that that's not the case. That was an idea we had a number of years ago, but it doesn't seem like that's the case. So how does this asteroid make dust? Well, look how close it gets to the sun. I mean, here's the orbit of Mercury is this pink one here. Mercury, we know, gets blasted by the sun so much that atoms just get ripped off the surface and float out into space. So imagine what this little rock swinging around the sun at a quarter that distance or so gets, the heat must just bake it and it just cracks and pieces literally flake off of it as it goes around the sun. And that's where all of those, that's where the dust bunny comes from. The great thing about this is that those dust pieces are much bigger than the dust pieces from comets. They're more substantial. That means when they hit us, they make brighter meteors. The Geminids, pound for pound, are one of the brighter meteor showers that you can see. That means, first of all, they look cooler. You can see them more easily. You can see them even from inside the city to some degree because there's more bright ones happening, and those will penetrate the light pollution, or they'll penetrate the moonlight because when the moon is in the sky, that's light pollution that you can't drive away from. And the moon is usually the death knell of a meteor shower. If it's full moon near your meteor shower peak, most astronomers will just not even bother. The Geminids are different. You can go out no matter what the conditions are and expect to see a reasonable meteor shower. Here's another thing about this particular shower. Phaethon is quite inclined to the orbit of the solar system, and it comes in from up above the Earth, and it comes in almost from in front of the Earth. And what that means is that as we go into this cloud, the meteors become visible earlier in the night. You can start seeing meteors of the Geminids as soon as it gets dark. You don't have to wait till 3 or 4 or 5 in the morning for it to get to the best. Actually, the best is around 12:30, 1:30, something like that local time. That'll be when the meteors are sort of at their best. Even with moonlight this year, the peak of the Geminids are expected to be 30 to 50 meteors an hour, which is pretty impressive. That's worth getting up for. Except it's December, so you have to weigh a little bit there. But there's no mosquitoes, did I mention? You can dress for the cold. You cannot dress for mosquitoes. We'll talk a little bit more about observing them after we get through the other showers here. So the Geminids, a wonderful little meteor shower. It turns out that the orbit of the comet, this white line, doesn't exactly cross the Earth's orbit. And that's wonderful because that means Phaethon is not actually going to hit the Earth. But the flakes that get broken off of it sort of float down in this view and make sort of a cloud that we pass through the edge of. And so this is the best situation. You got an asteroid that comes close to the Earth, but not close enough to be dangerous, but close enough that it gives us this wonderful meteor shower. This is what we think Phaethon is sort of shaped like. The image on the left is sort of a side view. The equator is across the middle. The image in the middle is also an equator view, except rotated 90 degrees. So we're looking just sort of at the other side. And then the one on the right is a top-down view. So this kind of looks like a, I don't know, like a dreidel or a top or something like that with a pointed tip. And it goes around like that. We think that it's probably all covered with cracks, and we think there's probably a lot of loose material on the surface as well. We don't really know that because we can't see even this well. These things are so small that we really can only see them as points of light. But the Japanese Space Agency has decided, well, let's go take a look. So launching in 2028 is, I forget what it's called. I didn't write down the English name. The Destiny probe. And Destiny is basically an acronym that basically says looking at dust on Phaethon. So it's going to go fly by this thing at only about 500 kilometers distance. And we're going to see what the surface of this unusual asteroid is like. So that'll tell us a lot more about how this meteor shower is happening and what's going on with this kind of weird object. So when do you want to go out? It's great that our meeting got bumped forward a week because we would have been sitting in this theater a week from now while the Geminids are going on over our heads, and we'd be sitting in here in a room with no windows. So it's kind of convenient that we moved. The peak will be next Friday into Saturday, and probably also just as good Saturday into Sunday. The true peak where we go through the center of the dust bunny sort of happens right in the middle there. And so either of those 2 nights should be good. as you can see here, there's Jupiter and the moon next to each other. Gemini is already over here by 8 o'clock. This is Gemini here. And then the radiant of these meteor showers is just off to the side of the heads here of Gemini, the twins. The radiant is where the meteors seem to radiate from. They go in all directions across the sky. But if you trace them all backwards, they would all seem to come from that one spot. That's the perspective that we get for this shower. And that's why they're called the Geminids, because their radiant is in the constellation of Gemini. So as the night goes on, Jupiter and the moon rise higher in the sky. So does the radiant here. And then Mars coming up afterwards. Now, here's the thing about meteor shower. They happen 30, 40, 50 an hour, but you can never tell what second you need to be watching the sky. And I don't know how many times I've been out and I'll be looking in my telescope eyepiece, or I'm talking to someone and they'll point over my shoulder and say, "Oh, look at that." And by the time I've turned, it's gone. You have to watch the sky consistently to really see these meteors. Or you're looking down at the eyepiece and suddenly you see the shadow of your head appear on the ground as the whole ground lights up. And by the time you turn to see this giant fireball, you've missed it. As tempting as it is to be looking at Jupiter or Mars or the moon or other things, if you want to see the Geminids, you basically have to watch the sky. And basically the peak occurs as Gemini gets to its highest point in the sky around 1 a.m. or so. I'm saying 30 to 50 meteors an hour. 50 is the very lucky side. 30 is probably a better range. If the moon wasn't there, we'd see probably 4 times that many. So this is a great meteor shower, definitely worth watching. Lots of bright meteors. And also because of the geometry of things, the meteors tend to trail across the sky quite long. They're not little short streaks. They're nice, long, bright meteors. So maybe if you're lucky and someone says, "Whoa, look over there," if you're really fast, you might turn fast enough and be able to see the end of it, because it might last, 1.2 seconds instead of only 0.8 seconds, something like that. Unfortunately, you can try and wait until the moon sets, but by the time the moon sets, basically the sun's about to rise. So this isn't the best year for the Geminids, but it's still good. It's still worth going out. And I got to tell you, if it's not clear until middle of December, and it's clear that night, I don't care how cold it is, I'm going out, because going into withdrawal here. So these meteors, Geminids is a great one to watch. There are a couple of other showers that happen at this time of the year. The next one that will get listed on most Facebook pages or whatever is the Ursids meteor shower. The Ursids, this is a weird meteor shower. It comes from almost right by the North Celestial Pole. There's Polaris at the top. This is the Ursa Minor, the Little Dipper. Big Dipper's over here. And so they're coming down almost right on top of us. These come from a comet's 8P, comet Tuttle, which goes around the sun every 13 years or so. And it's got a long oval orbit, this white line here, just like the other ones. It doesn't really get that close to the sun, though. It's a little less dramatic as far as that goes. If we look at the side view, though, it's coming in at a very steep angle and plunging past the Earth. So this one gives us that rare situation where the meteor shower's radiant doesn't really change all that much over the course of the night. It's always right by the North Pole, basically. So you want to go somewhere where you can basically have a nice dark sky, and you can go anytime in the evening, anytime in the morning. The time doesn't really make much of a difference for the number of meteors that you see. This is also a relatively new shower. It wasn't really classified until 1946. Like the Perseids have been around and observed every year for 2,000 years or so. The Ursids are very, very new. So that's kind of unusual. Now, it doesn't have a huge number of meteors. The average rate might be between 5 and 10 an hour, which is, I don't know if that's a shower really, but what's interesting is the dust bunnies that we're going through are not uniform. There are some little clumps in there. And every once in a while, the Earth will go through one of those clumps, and instead of 10 or 20, you get 50 meteors an hour for a couple of hours. So this one has some really interesting behavior that we really don't know all that much about. And so much as, just going out and looking at the sky is fun, if you go out and you count the meteors that you see, you can actually submit that to the International Meteor Organization or someone like that, and they will use that data to try and figure out why this meteor shower is behaving so differently from some of the other ones. And it's a pretty easy way to do science. You don't need complicated cameras or computers or things like that. The best accessory is a reclining lawn chair and a thermos full of something nice and hot, and probably about 3 or 4 blankets. So pretty easy to get into. Oh, and sorry, the Ursids are called the Ursids because their radiant is in the constellation of Ursa Minor. So that makes sense. Then we come to the Quadrantids. So what constellation are the Quadrantids in? It's a constellation that doesn't exist anymore. It's called Quadrans Muralis, and it's up above where Boötes is, sort of towards up above the handle of the Little Dipper. There's almost no stars in there. Whoever made the map basically was just filling in space, I think, and came up with these constellations. It's basically been dropped. But I guess no one could figure out how to make the Boötes sound useful. So the Quadrantids is the meteor shower that happens in the first few days of January. And it's another unusual meteor shower. It comes from an asteroid as well. So the 2 best meteor showers of the year both come from asteroids instead of comets. This asteroid has its ecliptic or elliptical orbit. It loops around the sun. It also comes in extremely steeply. It's kind of hard to see here, but basically it comes in at about 75-degree angle to the ecliptic, to the orbit of the sun, the Earth around the sun. And so it plunges through the solar system very, very quickly. And similarly, any particles that came from this object are also orbiting and plunging through the solar system very, very quickly. This shower, from start to finish, is 16 hours long. The other ones, it's like a week or so, it slowly builds up, and then you get to the peak, and you have a couple nights at the peak, and then it fades away over another week or so. This one is 16 hours start to finish, and it can peak up to well over 100 meteors per hour. Will we see 100 meteors per hour? No, because those rates are what are called the zenithal hourly rate, the ZHR. That's the number that if you were in perfectly dark conditions and you had perfectly good vision and you had 0% obstructions of the sky and the radiant of the meteor shower was directly over your head, you would see that many meteors. That's never the case. This is my backyard, and you can see that there's a significant percentage of the sky obstructed by these annoying things like buildings and trees. And that cuts the sky down. And the radiant, if it's low in the sky, the meteors that are coming up this way will be up above the horizon, but the meteors that are going down that way, you won't see them because they're going down below your horizon. So the lower the radiant is, the fewer meteors you see. And then, of course, there are lights and all those things. And the brighter the sky is, the fewer meteors you see. This was the one and only Perseid that I saw 2 years ago from my backyard. And my backyard is, in suburbia, but it's not terrible. I don't have any direct lights shining into my yard right now. And I only saw one. So that can be pretty disappointing if people think that there's going to be this big event and then they see something like that. When I went out for the Quadrantids, and please excuse the weird color cast, I pulled these off. This is from 3 years ago. And I didn't process any of the pictures really, and you can see that there are some little snowflakes floating around. This was almost a full moon night. And you can see these little streaks here. The quadrantids are moving so fast that they just go and they're gone in an instant, and they burn up very, very quickly. They don't have a lot of, stretching across the sky or things like that. But there can be lots of them. So I was out, all of these images come from within an hour in Birds Hill. And there are plenty of these little meteors and some other fainter ones you can't see. But the quadrantids performs really, really well on the years where that 16 hours happens when it's dark here. I mean, that's less than a day. So if the 16 hours happens during our daytime, well, we're not going to see it. This year, it's kind of half and half. We'll see maybe a little bit of it, but it's not the best year for the quadrantids. And also, so I mean, the Geminids will be affected by moonlight. The Ursids will be not affected by moonlight, but they're the least active of the 3 showers. And then the quadrantids are somewhat affected by moonlight, but also by the fact that they're very short and we won't see all of the activity in a dark sky. Still worth getting up and going out for, though, because the meteors you see are beautiful. Sometimes they can be very bright, and you never know when there's going to be an outburst. Even in regular showers, you can be sitting there and not see anything for a few minutes, and then suddenly it's like bang, 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 bang. They don't actually make a sound, sorry. But it can be very, very cool to see these things. It doesn't require any major equipment. You have to dress warmly, obviously. All the winter observing tips and tricks have to remain there. But it's also a great way to get into just sort of social observing. The best way to see a meteor shower is with a bunch of people. Go somewhere dark, find yourself a good spot, set up, and even if you don't see any meteors at all, you'll see the amazing winter sky, all the bright stars, the Milky Way, and conversation with all your friends. It's a wonderful way to observe the sky. All we have to do is make sure the clouds go away. Let me see here. And that's it. Any questions? Comments?
Probably a dumb question, but it's the beginner section, so not it. Because the comets or asteroids are captured by the sun and they orbit continuously, when they fade out, do they go out in a pool of amazing dust? Meteor shower?
Oh,
They just disappear.
like when a comet sort of runs out of the material. The question was, when a comet goes around the sun enough and its material is all burned off, essentially, does it go out in a flash, or does it sort of fade away? We don't know really, because we only happen to see examples of comets that are active, and then objects that might have been comets but are not active anymore. There's a big, actually, there's a citizen science project going on with NASA where you can look at asteroids and basically report if any of them are having cometary activity, because that crossover between comets and asteroids is kind of unclear. We used to think, oh, comets ice, asteroids rock. Way more complicated than that, and there's this spectrum of materials and sizes and things like that lead to it's just more complicated. And so observing meteors is one way to get information about that kind of situation. Good question, Michelle.
Science. Are you building time, number, or?
Yeah, so to do science with meteors, basically you write down the time you start watching and you record the time anytime you look away from the sky, so you can actually figure out how much percentage of the time you were actually seeing the sky. And then you count meteors. Most people recommend sort of 15-minute increments so that you can figure out as the rate goes up and then goes down. You can do more complicated things. You can plot them on a star chart. That takes a little bit more time because you have to look down at the star chart. You can use a camera, of course, or a video camera. All of that stuff can be submitted to the meteor organizations. And it helps, it's basically doing a census of the dust bunny that's out there. So easy to do and lots of fun. Okay, I'll throw things back to Dennis. Thank you.
Here you go.
And again, thank you very much to Scott. So for his talk on winter meteor showers. Dun, dun. Was there any questions in the chat for you, Scott?
No.
Okay. So again, tonight, welcome everyone. Just check my time. Yeah, we're already on time. Perfect. So again, thanks to Scott for the beginner session. Just welcoming everyone again tonight. For those that just joined us at 7:30, welcome to the RASC Winnipeg Centre's annual or monthly meeting. We'll talk about a few announcements shortly. We'll have What's Up with Brian Stock and What's New, Jay Anderson, short break. And then Gilles Ferrand will be our main presentation today, talking about the intriguing nebula PA30 and the supernova of 1181. So just go through a few things. Just a reminder about the Lockhart Planetarium here at the University of Manitoba. They have a public outreach event once a month, and if you want more information, please reach out to Danielle Pahoud. Fundraising committee, Wing Kwong is the chair of that. And Wing, you have a bit of a fundraiser going on here tonight?
Yes, $10 for a nice little red flashlight, 3 modes, and throw in a Duracell premium battery as well.
So for those who may not have heard it, he's got a really nice red LED flashlight for sale tonight. And yes, for $10, I believe, correct? $10. Explore the universe. Stan, anything you want to mention or just?
I was just gonna say the Explore the Universe, I'm working on a workshop right now called Star Hopping. And the Explore the Universe is gonna be thrown into it as a good part of the beginner session. Explore the Universe is for beginners. So we'll talk about a whole bunch of the objects associated with it. So rather than anything individual right now, I'm working on the workshop and it's getting bigger and bigger and longer, and I'm writing more and more. So it'll probably be more, it'll be in the new year before I be able to present it. But for those who are doing the Explore the Universe, when I get the final date of the workshop, I would suggest that they want to sign up for that session.
So for those that were online and may not have heard that, in the new year, Stan will have a session based on star hopping, but it'll be using the Explore the Universe. So anybody working on their Explore the Universe, highly recommended that you look at signing up for that workshop. And for anyone who's a member of the RASC Winnipeg Centre, that's a free workshop. So it's only available to members of the RASC Winnipeg. Telescope loaner program. If you're interested in borrowing one of our telescopes, we have, you can reach out to Mike Caracas. And actually, I'll ask Stan to come up and talk about our most recent edition. Is Mike here? Oh, Mike. So as they argue about who's going to come up and talk about our latest edition, I'll just pass the mic over to him.
Oh, yeah.
I'll carry it.
Okay, I've been around in astronomy for quite a long time. So as a result.
Long time.
Yes. Within that time, certain changes have occurred, and you can sort of see that these changes are coming and they're occurring monumental. One of the ones, for example, was back in the 70s, I think it's just early 80s. All of a sudden, a company called Celestron started to make these nice little small little scopes, and they became the rage. You could sort of tell at the time. Prior to that, people were building their own ATM was the big thing. making your own telescope, a reflective scope, and going in the air and building it. Then this scope came out and it took off like wildfire. There's another occurrence that happened with digital cameras. All of a sudden, digital cameras came in. It changed the whole astrophotography aspect of things. There was a gentleman called James Dobson, John Dobson. John, who kind of changed the reflector telescope, building very, very large mirrored scopes and making it very simple for people to build. Like you get the big mirror and it changed the whole industry. People were just rushing to have Sonian scopes. We have 2 of them in our loaner program. And they're both out right now?
One's back, this look there.
Okay, so for people who want to experiment and try that kind of scope, we have that one available. Well, there's a new age that's coming on, something else that's happened, and that's these new electronic, what they call smart telescopes. Now, I think the smart part is you got to be smart to be able to use them. They're not quite absolutely spectacularly easy to do, but they do get people involved in the imaging of scopes, imaging with scopes very quickly. Here's the key. These don't have eyepieces. This telescope here has a camera built into it and has a system that you run totally off of your phone. So you load up a software package onto your phone. There's a software package in this. We turn it on. You can have it pointing at objects and taking images for you. It will take images. It takes very short images and then stats and integrates them together, combines the light from one picture to the next, and builds up the image. And over a period of time, you keep capturing the light from the same area at the same time, and that object becomes brighter and brighter and brighter on your phone in the image that it does. I have a different style of one, it's like Warp 3, but with that one, when you start to run 15 minutes of running an image, then you stop, it takes all those images, does that, it even will provide you with a thumb size image, they'll provide you with a small JPEG showing you what the whole combined image is. And it captures all these other images. So this is the rage. This is where astronomy is going right now. These things are if you can get them, there's some of the newer models that you can't even get. There's not a lineup, not a witness. But this is the scope of the future. To get people interested in it, hopefully they come to the first point where they will start replacing the jump scopes that are out there. So this is the club scope. We're going to have in order to get this, you'll have to be a member for a year. You've got to load your own software. You've got to use your own device to connect to it. We've got some restrictions, and it'll only be available for a month at a time, and we will try to pass it around. So is the person who's going to get it for the first month here?
Yes,
Is he excited? No, not even listening to me.
not even listening to you.
I'm talking with you. You're getting this first, correct?
Yep.
Yeah. See, you can tell how exciting it is. It's almost cool. So, people who want it, contact Mike. He will be the one digging out how it goes. So we're going to try to get it to as many people as possible. So this is as people have mentioned, this is the reason why it's been cloudy. We just got this a couple weeks ago, and it's been up to about 6.
Stan, when you maybe mention about the temperature restriction.
Yeah, one of the things that we read about it is that there's a temperature restriction of using not to be used below -10 Celsius. So and that's because of the battery pack. What's the temperature for tomorrow?
Well, be clear, it doesn't matter. It was boring clouds.
So, by the way, it's got specialty modes in it for deep sky, and it also has a mode for solar system. So it will do pictures of the sun and the moon, and it does actually quite high quality pictures. And this. You see this? Oh, okay. You guys see that?
We can see your phone out of focus.
Okay.
All your contacts. All your.
Yeah.
Yeah, that's what I wanted to show you. That was a picture of, for everybody else. It's a picture of the sun that I took this past summer. Which one of these units? It's actually like a capable little instrument. So anyway.
Well, I think what Scott was getting at, that if you went to your banking page, it'd be easier to focus, and then you can go to the picture.
Yeah. Anyway, that's the, I thought the whole time you guys had arranged to show the,
You did.
I guess.
But
then I cleaned it back when you stopped. Okay.
And I'm not sure if Stan actually mentioned, that's a C-Star S50 that's available. Thank you very much, Stan and Mike, for talking about it and for doing the research of what we should be picking up for the club. Again, it's another member service that for those who are members of the RASC Winnipeg Centre. And somebody mentioned down here, Stan, they're just wondering if you were around when that new comet or the new meteor shower came out in 45? No? Okay. All right, I'm just passing on the questions for those there. So just continue on here. Again, Stan, he has already mentioned there that one of the first workshops in the new year is for star hopping with a slant towards explore the universe. Nominating committee, so myself and Scott Young are on that. We are recruiting for several positions, president, vice president, treasurer, counselor. So if anyone is interested in those, please let either one of us know. Member observing night is obviously going to adjust to sky events. We'll talk about that shortly. Anyone who has had purchased a calendar, Stan has them, and you can just see him and make arrangements to pick up and or pay if you're still outstanding for payment. Our annual general meeting is on the 14th of March, 2025, where we will have the elections, the financials. And again, the reason it's later this year is to allow our financials to be fully completed to comply with our incorporation documents. Stan.
We're going to do some, there's another workshop that's being. So.
So we're just waiting for James to come walking down here.
Just wanted to let you know, we're working on another workshop, a stellarium, introductory to stellarium kind of workshop. That's planning right now. We're planning that for January the 9th, a Zoom workshop. So national, some of you may know Blake Nancaro out of Ontario. He unfortunately passed away about a year ago. Blake did a lot of online training with stellarium and a few other programs. National has started that up again. But I found that they're hard to register for. They fill up pretty quickly. So I was chatting with Scott, and what we'd like to do is do that for the Winnipeg Centre in January. We'll run it as a Zoom kind of workshop. It'll be very introductory, how to load. Well, there'll be some instructions, some more information. But if you just want to put on your calendar, if you're interested in that, January the 9th, 7 p.m. It's a Thursday. We'll send out more information. We'll go through how to use stellarium, how to move around, how to maybe load comments, and just kind of how to use the program or whatever. If it interests you, Thursday, January the 9th.
Thank you, James. Telescopes for kids. Wing, did you want to speak to that for a moment? So as Wing makes his way down, Telescopes for Kids is a program where we raise funds and for telescopes that we then encourage kids to tell us why they would like that, what they would use it for, and then present them to them without any charge to them. Wing.
Yeah, just very briefly, there's a new edition, 2025 edition of Telescope for Kids. All the information that is current is on our website. Just click on the Telescope for Kids program. And in there is a link to a GoFundMe campaign. And so I encourage you to check it out. and contribute to a very worthy cause. Thank you.
Thank you, Wing, for organizing and running that this year. Our holiday potluck that's a lunk, is on the 18th of January. It's at the Lounge Co-working Exchange on 167 Lombard, and that's behind the Grain Exchange building. So there'll be more information be sent out, but the date, so you can put it in the calendar, is the 18th of January. And again, that's a RASC Winnipeg members get together. Again, just groups.io is our primary means of communication. And I would suspect that that's where the workshops, once they'll be advertised, and then the workshops will tell you where to get more information. And it's usually found on groups.io. Our next members observing night is tomorrow night at 7 p.m. at Glen Lee. And just before I introduce Brian Stack, I just need to ask you all, what do planets like to read? What do planets like to read? Comments?
Oh.
And please welcome Brian Stack.
I'm done.
Sorry. We have a laser phone. That one. That's okay. Maybe. Is it really okay?
Just as a quick clarification, the member night is scheduled for Saturday, December 14th. We did that because that was the jam.
No, I got a English here.
The members observing it. Was that who's running that one? Is that Judy? Yeah. Okay.
Just gonna share the screen. Okay, it should be good. Yeah, and just those two keys for them.
Oh, okay, not the mouse pads. Yeah, try this. Okay. So let's find out what's up for December 2024. There's a few things interesting going on. Some meteor shower, as Scott has kind of mentioned about it, but of course we are competing with the full moon. Okay, we'll start off with the planets. I'm going to use the keys. Okay, so right now, of course, Mercury is a little too close to the sun to be observed, but later on in the month, it would emerge into evening apparition here. Venus is quite low in the sky, in the evening sky. Mars is going to reach stationary in December the 7th. We're catching up on Mars. I'll go a little bit more detail about it. And it will begin its retrograde motion in January the 16th. The size of Mars is not too great. Again, I'll talk more about it later. Jupiter will achieve its opposition on the 7th of this month. It's going to be quite visible all night and all evening and throughout the rest of the month. And of course, Saturn would be quite visible in the evening sky. And okay, so you can see there's quite a bit. I'm going to step away this time. All right. So, of course, we have the new moon. I kind of noticed this month here, we got two new moons, December the 30th and December the 1st. Of course, as I mentioned, Mars is going to be stationary as December the 7th tomorrow because we're catching up on it. Okay, and of course, we have the first quarter on the 8th. Saturn would be just 0.3 degrees south of the moon. We have the Gemini meteor shower on the 14th, but as you can see here, December the 15th we have the full moon, so it's going to be pretty much washed out. Of course, we have the winter solstice, and this is what's classified as being the first day of winter. The last quarter is on December the 22nd. We do have a meteor shower on December the 22nd, Earth's meteor shower. And I think the moon doesn't come up until 1 a.m., I believe. So still a bit of a chance to look at it. I'll talk a little bit about the double shadow of Jupiter on December the 23rd. Starts roughly after midnight and goes out the whole night. And of course, as I mentioned, we have the new moon on the 30th. Okay, as I mentioned, I'm going to talk about Mars. I did look at the data apparently for the last 79 years. Just kind of see the distance between the two here. So I got 3 diagrams going around here. This bottom line here is not really up to date, but it gives you the pattern how it starts off really big, December or like 2003 at 25 arcs across. And then every 2 years, it gets smaller, 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 up to the point where they start getting bigger and bigger and bigger. That's the pattern of Mars. This is because of the orbit of Mars. You can see here, blue represents Earth and red represents Mars. You can see it's not exactly, it's more elliptical in pattern here. And of course, on this part of it here, Earth, see, it's a little bit of a tilt between the two. So it depends upon where it meets on each of every 2-year cycle. But I did look into this paper in the 79 years of Mars. You know, someone said it comes right back after every 79 years. So I'm going to start reading more about that paper. I thought it was kind of interesting to see the pattern here. Okay, so this time around, January the 16th, it's only going to be like 14.5 arcs across here, right about here. So next 2 years, it's going to drop down just a little bit, and then the cycle is going to go back up again. So I think was it 2035, 2040, something where it gets back up to 25 arcs, which is a long time away. Okay, now I think this is actually this evening here, just kind of point out some of the events that's happening here. We do have, of course, the Orion constellation here. We have Mars here. What I mentioned here, of course, we have the Pleiades, Jupiter. It's going to now, one thing I kind of noticed here, I made a note here above 62 degrees above the horizon around 11:30 after I came back from the gym. Now, this diagram doesn't really justify how high Jupiter really is. It looks like pretty high, but when I was out there, Jupiter was pretty much almost overhead. So again, it's pretty high. And what does that really mean for observing? Because there's less atmosphere to observe. So if you are going to be observing Jupiter, this would be a good time. And it's a little warmer if it tends to be clear, which the weather doesn't look like it's going to be holding out. Okay, so tomorrow evening, as I mentioned, we have Venus here, low in the sky here, just after sunset. We have Saturn just a few degrees off of the moon. And Mars is not too far behind. Now, I did mention about that meteor shower. And it's Ursa, I believe. Gemini, sorry. Did I say Gemini? Ursa? Gemini, sorry. It's Gemini meteor shower. Okay, so it peaks on the 14th, I believe, right? Around 1 a.m. Of course, Scott kind of mentioned about this is not really a true value, depends upon where you're at Earth and where how it's hitting the Earth and all this. It's as he's mentioned it before. It varies. Of course, realistic here in Manitoba, we only get 4 or 5 per hour. Of course, and then what I mentioned before, it's like we have the full moon on December 15th, so that's pretty much done. You know, with the warmer weather, it would be kind of nice. Now, the Ursa meteor shower, as I mentioned, good chance. The moon doesn't start to rise until 1 a.m., so not bad. So there's again a chance of it. Only again, it's rated 10 meters per hour, but again, that varies from experience. So it's not always 10 meters, it might be less, it might be more. We'll just have to wait and see. Hopefully the sky is going to be quite clear. Now I have here December 23rd, I'm not going to mention about again, the double shadow transit of Jupiter. Now it starts here at 1:52. I know the calendar says 2:47 or something like that, but here it's 1:52 where the double shadow starts. Local time here, again, it's going to be quite high in the sky. Of course, we have the Orion constellation here, which is kind of nice. We have the Pleiades. Uranus is not really big on it, but but in my next slide here, I'll talk a little bit about the double shadow. Now it starts, the first one starts, this one here starts around, as I mentioned, 12:40 a.m. And then the second one will start around 1:48 a.m. And the last one, this one here will reach at the edge of here around almost 4 a.m. So pretty good all evening. Hopefully it's going to be warm enough and clear as always. Now, I'm going to start with the weather. And again, if anyone's been monitoring the weather like I have, at the start of the week on Monday, it was supposed to be a low of 12 this weekend. Now, as you progress throughout the whole week, the temperature starts to rise. So now we're up to what, +4 tomorrow. I just looked at the weather again. It's supposed to be +2 on Sunday. Now it's +0 or 0. So again, but it will get colder again for the next week. So, and for the clear skies, again, this keeps changing. So it was supposed to be relatively nice tomorrow, but again, look at the forecast tomorrow. It looks like it's going to be cloudy, unfortunately, but warm. But I have an event to go to tomorrow, so it really doesn't matter for me. So I think that's it. That's all I have to say for what's up for December 2024. Thank you. Easy walking around.
Thank you, Mark. And we'll just welcome Jay Anderson up to do What's New. Please welcome Jay Anderson.
There you go, sunshine.
Thank you.
And I turned on.
It should be, yep.
Yep, it works. Got it.
Yeah. Just need 1 minute here.
I already see there's things that aren't working on this.
Here you go. Here. Okay. Okay.
Disconcerting start to this because I see 2 bits of print that are supposed to be in and aren't here. But anyway, today's What's New is a little bit different in the sense that it's not an earth-shattering major discovery, but it's a project that's entirely amateur driven. And it's called the MDW H Alpha Sky Survey. You might have heard about this. There's been the odd note about it in Sky and Telescope magazine. Not surprising because you can see the 3 people who founded and actually conducted this project. 2 of them, Dennis DeSico and Sean Walker, are both well-known editors in Sky and Telescope magazine. David Middleman was also a partner, but David unfortunately died in 2017 as the project was well underway at the time. For those of you who aren't familiar with H alpha, hydrogen in the universe gives off light if it's stimulated by energy from a nearby star, and that light can be in a large number of wavelengths, but one particular wavelength in the deep red, 656.3 nanometers, that wavelength is sort of ubiquitous throughout the universe, throughout our galaxy in particular. So everywhere you look in the sky, there's hydrogen emission, hydrogen alpha emission coming toward us. And you can see in the bottom here, I better keep an eye on what shows up. In the red here is a picture I took years ago with a special filter that isolates that very, very narrow wavelength of light in the red. And it's a wavelength that's visible to the eye because we can see it when we put hydrogen alpha filters and look at the sun, but it's pretty far gone. And so cameras don't record that red wavelength very well unless you have them modified. In black and white, there is the same object. So this is an object in the southern hemisphere. So their goal was to get a high resolution survey, study, image, if you must, of almost the entire sky in hydrogen alpha light. And you sort of think to yourself, well, pros must have done that a million times.
And what they use is equipment that's pretty familiar to most of us who spend their time drooling through the pages of the sky and telescope or searching online. Astrophysics refractors, a 5-inch, a fairly fast one. They put in a compressor on it to make it even faster so you could get short exposure. They used a CCD camera because this project started back in the 2016 era, and CMOS cameras weren't quite so popular at the time. We'd probably use a more sensitive one if you're going to do this again. They had a 3 nanometer filter at 3 angstroms, if you want to use the old term, so extremely narrow filtered light. And they had 2 sites that they used, one in the northern hemisphere, one in the south. They had 2 telescopes in the northern hemisphere in New Mexico, Middleman's Observatory. His family foundation actually funded the start of this project, but since that time, there's been money put in by the European Southern Observatory. And all the data they are collecting is housed at Columbia University, where you can go in and get it. Well, how hard is it to take a picture in hydrogen alpha light? The 2 that I showed you were taken with a 50 millimeter lens, and they were about 12 minutes exposure. So what's so special about what's happening here? Here are your technical details. This will mean quite a bit to most of you. 4 hours for each frame. Well, this project to photograph the whole sky is over 4,200 frames. So we're not talking the wide angle picture from the 50 millimeter lens that I showed you. We're talking a narrow view from a telescope, so that to cover the goal where they had to collect 4-hour exposures for 4,200 times. And of course, there's a lot of little errors that creep into these exposures. So you're actually probably getting half again as many photographs to be able to cover things. You can see the field sizes and bias and dark frames. Those are calibration frames that they have to take. And everything had to be calibrated because they're not only looking at the nebulosity that shows up in these images, they're also looking at every object in it that shows up in hydrogen alpha, which will be tens of thousands of stars for one thing. And every one of those stars had to be identified, calibrated as to its brightness, and a giant catalog made, so that researchers, and this is designed for professional astronomers, so that researchers could go back into this catalog if they wanted to search for some peculiar object or see if some object that they were finding had a hydrogen signature. This is what the telescopes looked like in the New Mexico site. There's some very nice equipment there. I would imagine that each one of those telescopes is probably $15,000 or $20,000 American. But if you get funding from another agency, then you get a long way ahead in being able to afford this sort of thing. You'll notice that they made special attempts. These weren't your casual, I'm going to go out and look at Jupiter tonight and tomorrow I'm going to do this photography. They wanted to seal these telescopes up as much as possible so that every night the behavior, the focus, all the characteristics of the telescope were identical, so that they could match up the frames when they got to the point of adding them together. This is the series of objects in red there. That was what they call their D0, DRR0. That's the test area that they wanted to do first. And each one of those little squares is one of the sectors that had to be photographed. Well, that red area encompasses the Orion Nebula and a few other things. And so the blue line is somebody else's previous study in hydrogen alpha photography and the area that we covered. The blue area is their DR1, which has now been released. And the reason why it's a current news item is because this massive Northern Hemisphere hydrogen and alpha database is available. And in fact, much of the Southern Hemisphere is also completed now. They're just not quite ready. I think next year is when they're going to have to put out the DR2, and that will be then have completed the entire project with all of its images. And every one of these images is available, calibrated online at Columbia University. So what are the processes that they follow? They're primarily interested in nebulosity, but they also want to know what the stars are. So what they did initially was take the original and remove all of the stars from it. Here they are, these black dots in here are where the stars are in the image. And then they were able to process using just the nebulosity, just the H alpha signal from the gas in our galaxy. It makes it a lot easier to do. You put the stars back in later on. It's a common enough technique when you're processing imagery. You would like to be able to, the nebulosity is hard to bring out. You have to often use fairly extreme measures of enhancement to make it visible. And that kind of enhancement, if you do the same thing while the stars are in it, the stars will usually be overexposed and you lose the signal, the intensity information that comes with them. So once you've done all this, you can see 238 fields in the DR0. Well, right away you're learning that taking the pictures is one monstrous task. Processing those pictures is another monstrous task when you have to go through all of this procedures. And there's flats and darks and bias frames that also have to be used to calibrate them. So when you take these frames, here's two examples of what happens with the processing they have to do to make mosaics out of these. So here on the left-hand side, we have individual frames, different exposure, similar exposures, but different amounts of intensity for one reason or another. But with the right kind of software, you can bring them all together so that they are evened out. All of the differences between the frames are corrected. They used as often as they could commercial software to do this, but for these processes that require on such accurate calibration, they actually had, in some cases, people they knew wrote special routines for them to make this much more correct. You and I can make mosaics out of our pictures and we can do a little bit of extra darkness in the background so that the divisions between the frames don't show up. In this case, you had to be much more rigorous. So here's your DR0 field. And you should be able to recognize some of those things. You can see the little box here with the upper right image is the Orion Nebula. That shape is fairly well shown. You can see over here the Eridanus loop, which is a structure that shows up sometimes if you go out and take a picture of that part of the sky with just a regular camera, but it's pretty faint. Then we can see other things like the Cone Nebula here on the left-hand side and some of the other important things. I think the one thing you learn right away, if you didn't already know it, is that some of our most familiar objects in the sky that's coming up right now, particularly in the morning, is that it's an enormous amount of hydrogen gas in those areas that we often don't see because our exposures are too short. So in this particular example, they've stretched the image a little bit to make it more visible. But you can see that when you zoom in at like the Cone Nebula there on the lower left, that you've got some quite considerable amount of detail as befits photographing with a good quality 5-inch refractor. I should point out that astrophysics made sure that the refractors were very carefully matched when they bought them. Well, why do they want to do it? Well, here on the left-hand side is a frame from this project. And the center and right-hand edge pictures are from previous H-alpha studies. Their names are given there, SHASA and VTSS. But look at how much more resolution you have from 3 amateurs with a 5-inch telescope who are prepared to take the thousands of hours necessary to do a project like this. And it's for this reason that these data have already appeared in several professional publications with authorship given to the 3 proponents of this project. A couple of things, just to sort of examples to show. Here's the Magellanic Cloud, the Large Magellanic Cloud. There's a picture over here of what it looks like visually that Judy took last month. It's not the same. I mean, look at what's in it. The resemblance between that image and this image is fairly indistinct. This one's rotated a little bit by about 90 degrees, but all of those little puffs in many cases are old supernova explosions or little bits of nebulosity like the Orion Nebula and things like that. So if you get a rounder shape, you can start thinking, oh, so there's supernova explosion there. And if nobody's noticed that before in some other kind of field, you want to study them, you could go pick out probably 12 supernova explosions out of this in the Large Magellanic Cloud that you might want to have a look at. This is an interesting feature. This is in Ursa Major, the Great Bear. Take one look at that and something jumps right out at you. What's that straight line? And I thought, oh, somebody's got a hair across the camera. But it isn't. It's real. And it was known before this image was taken and some of the others. But nobody was aware of its enormous extent because it goes way beyond the edge of this frame. And in fact, it looks like there's a sequence of little lines parallel to it here. And so this was an interesting paper. When you look at it, the yellow arc is what showed up in that picture. And over there in the lower right, I have a separate image. A previous discovery in a far ultraviolet, and it's not the white line. The white line is to sort of draw your eye to it, but the actual arc is those short segments of arc just above it. The white line is kind of show you where to look to see it. So there's some speculation that this is compressed gas from some kind of a shock wave, maybe a long ago supernova explosion in the center of this circle. But so far, nobody's been able to identify anything in the middle that this might have come from. You look at Cygnus. Many of you will recognize the North American Nebula and the Pelican Nebula here. Probably none of you photographed it to that depth. I did take a picture once of that area. I like this one because of its wide angle. This is a whole bunch of sorry, this is not. I want to go back here one, just so you can take a look at the detail in here. The North American Nebula in the center, Pelican off to one side, and everything else. This is an H-alpha picture that I took with a 50 millimeter 7 or 8 years ago. And of course, in the top, you can see the North American Nebula and the Pelican, although not quite so recognizable. This is 12 minutes of exposure. So not only is this a nice project that they've done with all of the scientific calibration, but I think, you know, for the price of a H-alpha filter, which in my case was a 12 nanometer one, one of the cheaper ones, so they're about $250 each, and drop them in a regular camera and just do the exposures. You could park one of these, a camera on top of the telescope out of Glenley and just piggyback it, and you would probably have to take, unless you had a very fast lens. I have to thank Steve for loaning me that lens. But unless you had a lens as fast as that and could get this in 12 minutes, you might have to take 20 or 30-minute exposures. The thing is we can do this stuff as amateurs, but we can't do it well enough that the professionals would find it particularly useful. Under the bottom of this, you can see the Veil Nebula, and there are a number of other arcs in here that appear on to the right of the North American Nebula. You see the area around Gamma Cygni, which is a very, very nice area of nebulosity, though not as sort of visually attractive as the North American Nebula. Here we are looking at Orion, but now it's not that small sample of Orion. This is from the DR1, and you can see Orion is in that big circle in the middle is Barnard's Loop, and the upper bright spot is where the Horsehead Nebula is, and the lower bright spot is the Orion Nebula, and up above it is, well, there's all kinds of stuff in there. There's a Cone Nebula in there, and tons and tons and tons of stuff. So working in H alpha is really easy to do if you've done some astrophotography, but you also have to admire the amount of work these fellows did to put this together. So I hope it encourages you to do it. Thanks very much.
Like Dennis has just stepped out, but I guess we'll have a break now.
Have my permission to take.
If you could take your seats, please, we're going to get started. I'll just do your introduction. Okay, is this pointer?
Well, there is this, it's just for this screen here. It's just a cheap laser. Okay.
Oh, okay, cool. Okay, yes.
Video's on, audio's on.
So please sit down, we're going to start.
It should be good. Camera's right there.
Oh, okay. And is it tracking me?
No, it's just very cheap out.
At some point, I need to go to Yeah, those are here. Yeah.
Didn't like.
Okay. Let's do your introduction. Good evening, folks. I would just like to introduce Dr. Gilles Ferrand. He is a computational astrophysicist who has worked in research institutes in France, Canada, and Japan. His main research interests are in supernova remnants and particle acceleration. He's also a keen interest in scientific visualization. Please welcome Dr. Gilles Ferrand.
So it's good to be back. I think it's been maybe a decade since I last attended a meeting in person in this week, the RASC. And so I'm going to talk about supernova remnants tonight. So this is my typical, okay, can we move for, okay, yes, sorry. I want this out of the way. Can I not move this? Ah, yeah. Okay, I want this. No, wait.
There is a way under more.
Yeah.
Is there some in? It goes first.
Okay. Yes. Let's go full screen. So yeah, so that you can see everything. So this is my one slide introduction. And so I work on supernova remnants. So the remnants of supernova explosions. You have an image on the left, which is Tycho. We'll talk about the historical ones. And so these are important objects in astrophysics. This is related to the life cycle of stars. This is how elements synthesized in stars are delivered to the interstellar medium. This is also a place where particle acceleration happens. So what you see is a big hot bubble of plasma expanding over large, very large distances, over tens, hundreds, thousands of years and more. And so on the left is an observation. What I do myself, usually it's simulations. I'm more on the modeling side. And so on the right, that's an example. That's a volume rendering of the 3D simulations I've done of using some explosion models that could be maybe applicable to this remnant. And so, yeah, I do mostly numerical simulations and working with computers. So 3D simulations and also 3D visualization. And so tonight, I'm not actually going to talk about what I do most commonly, so the simulations. So it's going to be about remnants for sure. So, okay, I lost the focus. But so I'm going to tell you the story of a very peculiar remnant, a newly identified one, a new historical remnant with a very peculiar properties. And in a second part, I will tell about what I did with this object so far, which is to make an image of it, a composite multi-wavelength image. So it will be about the physics of explosions and also about image making. So like what are these images? So I think most of you know about this, but so I think it's important to understand what it is that we are doing, we are showing. Now a bit of, okay. Okay, so first, what's a supernova remnant? So you are amateur astronomers for the most part. And I gave a talk like 10 years ago on supernova remnants, so I suppose you remember. But so supernova, that's the explosion at the end of the life of a star. So life, yes, stars, they live and die. And so a star like the sun, about the size of the sun, will evolve towards a red giant, and it will have a relatively peaceful end of life. So it will eject its envelope, forming what's called a planetary nebula. So that's a misnomer. It has nothing to do with planets. The name just we stuck with it. So that happens a lot in astronomy. But so that forget about planets. So this is the envelope of a dead star, and the dead star remains as what we call a white dwarf. So very compact star. So it would be like the sun shrinks to like the size of the Earth, something like this. And so this will slowly die off. And maybe that's it. No, it not. If the star is much more massive than the sun, like about 8 solar masses, typically, it will undergo a more complex cycle of fusion of elements, and it will end up being called the red supergiant. And when it ends, the burning of elements, the star will collapse, and there will be what we call the supernova, so the explosion of the star. So really, supernova is the event. The star is like the stellar material is ejected, but something may remain at the center, a compact object, and so that could be a neutron star, so even more compact than a white dwarf. It would be like the sun shrink to like the size of a city. And it may have a magnetic field. It may be spinning also, then you get a pulsar. And it can also be a black hole. So then gravity wins, and you just swallow the star. So this is a core collapse mechanism, and we call it conventionally type 2 or 1b, 1c. So there is always this zoology in astronomy also, but so the physical mechanism is core collapse of a massive star. Now, if we go back to the white dwarf, actually that's not the end of the story, because if it has a companion, and it's quite common for stars actually to have companions. So if it accretes some more matter from a companion, it may also explode because there's a stability limit, a maximum mass. And so if it reaches this mass, it will go supernova as well, but completely different mechanism of thermonuclear explosion. That corresponds to 1A observation. Okay, there's two main channels, just as a reminder, maybe. And I said it's a cycle, so yes, let's close the loop, okay, because so again, the elements that are synthesized in the stars and in the supernova explosion, they are going to be delivered to the ambient medium, to the galactic medium. And this is from this new material that new nebulas will form and new stars will be formed that are enriched in heavier elements. And eventually the elements that make us. Okay, so this is not supernova remnant. It's not what I want to talk about, but it looks similar and it's related. So that's the end of a normal, say a normal star. And so they tend to be symmetric, sometimes a bit more complicated shapes. So these are, I selected some messy ones. So these ones you can see them with a telescope. Now, what I'm interested in are supernova remnants. So when there's an explosion of the star. And they tend to be also globally like spherical. So you have like point explosion, and you get ejectas that are expanding, and you get this kind of bubble. So you get a shell of shock matter that is expanding. And so this is, maybe the most typical morphology, the shell-like morphology. This is a cute one in the LMC or SLC. And you get different shapes also. So this Okay, still on this category. So usually the shell is the most visible, so the outline of it, but sometimes it's bright inside actually. And sometimes there is something inside which is because of the compact remnant. So I said you can get a neutron star, and if it's active, you can get what we call a pulsar wind nebula, or P-wind, or flaring. Okay, so the crab, you know the crab probably, and so that's a good example. And so this one, so what you see here is powered by what remains of the pulsar. You barely see the ejecta, you don't see the outer shock in this case. But so in principle, you should have both, right? And so this is an example of a composite. What you see inside, this is a pulsar wind nebula caused by the neutron star inside. And looking carefully, we were able to see the shell around it. So that's the ejected, exploded star. That's was the work of Heza Malleson. And so they come in different shapes and they evolve in time. And so they will have a variety of shapes. And we know like hundreds of them in the galaxy. And so if you want to know all about them, you can check our catalog, and you have them. So I said archive. So we have 383 records. There's going to be like at least 200 more soon. But so like it's in the hundreds. And they are not all equal. Like we have images, and some are looking good, and others not so much. It's quality of data varies a lot. Okay, and edge distance vary a lot also. And so we're interested tonight more in explosion physics, and so more into young remnants. Okay, the earlier you catch them, the easiest it is to say something about how it exploded. So let's look at young ones. And with young ones, you have something cool that you have actually historical ones. So meaning that we actually did see the supernova. Like sometimes like hundreds of years, thousands of years ago, people noticed a new star in the sky. That was actually not a new star, but like the last stage of a star. And so for weeks or months, they saw this, they record this. And then when we point telescopes now, we see the exploded star, we see the remnant. Okay. And there's just a handful of them really. So there's 4 that are really clear cases. So there's Kepler, Tycho, I will show them. Crab SN1006. There's a few more, like in the past 1,000 years. And there's a few more, like you can go back to like maybe a couple thousand years, and you have records that you can trust, but it's getting more and more difficult to match them with modern day objects, because it's like there was something over there, and like getting a bit tricky to make associations as candidates, suggestions. And also, there's some that we know are young, but we missed. So we have no record of the supernova, but we know it happened like in the past few hundred years. And we do expect like a 2-3 maybe per century in the galaxy, like Milky Way. And so the last one was 1604, so 400 years. So we are long overdue for next one, anytime. Okay, so let's have a look. Show some images. So let's start with SN1006. So 1006, in this year, we have records, Chinese records mostly, and others, of this like gas star, new star, which was as bright as a crescent moon. So you could see it even by day for a long time. And this is what we see now at this location. So that's a supernova remnant, the exploded star. And so that's a 1,000-year-old remnant. Okay, so let's not be confused about ages. So this is like distances are uncertain, but this is like 5,000-7,000 light years away. So really, the light takes thousands of years to reach us, right? So what do I mean here? Well, we saw like the supernova from our perspective. It was in 1006. Okay, so this is when it starts for us. So in 1006, we see the supernova. and now in 2000 something, we see a 1,000-year-old remnant. This is not how it looks right now. We have no way of knowing how it looks right now. It's not in our light comet. Okay. And so what is it that is shown? So this is going to be about images tonight. And so this is a composite image. So I think most of you get this. So this is not like a photography, like a photograph. It's a bit more involved than this. This is data taken with instruments, different kind of instruments that see different kinds of light. And so here you have X-ray data in blue. So this is hot, so that shines in X-rays. And you get radio data that's color-coded red. These are energetic particles also. And you get some optical also here, shown in yellow. So that's a color composite with different data layers for 1006. So then 1050 for the crab. Okay, so you've seen this one. And so this is a pulsar wind nebula. You see like it feels like an explosion. And this is still active, and this is because of what's inside. And so the pulsar inside. So this is Hubble's view. And on the right, you see what you can see with X-ray vision, so that's Chandra satellite. And you see this torus and jet. So this is around the crab pulsar. So nebula. And so this is HST on the left, and now we have JWST. Tycho, so I like this one. So why Tycho? So we have records from Tycho Brahe, so the astronomer. So that's him. So that's not from this time, but that's an illustration from Flammarion. And so people are looking at this new star, and so it's recorded Nova Stella. So this one, and so no, it's not really a new star; it's a dying one. So again, we look and we see 500 years after about this. So that's the exploded star. That's the hot stellar ejecta. And so again, this is a composite. You see X-rays of different energies in green and blue, and infrared in red, and the stellar field optical in white. So this is one possible image. This is another one. Because of the same object, but it's a different choice for the assignment of colors. And so actually many colors are used in this one, covering a wide range of energies in X-rays. And the thing that's most interesting in this particular image, it's the color coding of the silicon line, which is shown orange and blue. So the line will be shifted by the Doppler effect, depending on how it's moving with respect to you. And so this is coding the red shift versus blue shift of the line. And so moving away or towards us. And so you see this orangey patch versus this blue patch. So this, you see this is 2D, this is flat, but actually with this, you can tell apart which is moving in which direction. And you can see this is not, they don't overlap exactly, so there's some asymmetry here. So this is the kind of things we study to put constraints on the explosion physics. And so that's another view of the same object. Kepler, so again, it's named after a famous astronomer, 1604. And so we know both of these are thermonuclear explosions. So that was a white dwarf. One or two, we don't know. And so again, that's a composite with mostly X-ray emission. And this is the core collapse remnant we know because there's a neutron star in the middle. This is gas A, famous one also. So this one is a missed event. We know it's young, so a few hundred years, but we don't have a credible record. And this is again a composite with X-ray data, optical data, and infrared data. Again, typically X-ray, you see the hot stuff, infrared, more like dust, and the stellar field optical. And this one uses Hubble for the optical or near infrared, and this is JWST, infrared or near infrared. So two instruments, near infrared and a bit further. So this is to be compared with the one on the left is an improvement on the yellowish part, and the one on the right on the reddish parts, sort of. And so then the youngest one is this one, G1.9 plus 0.3. And so the age is estimated to be like 150, maybe 200 years. But so again, no record, but it's throughout the galactic center, it's crowded, so we may have missed it. And so again, composite, and you see all the radio and X-ray emission do not match. And you see these lobes. Let me show again quickly. Where is my... You remember this one also has lobes? That's because of magnetic field and particle acceleration. And let's go back to G1.9. Again, two different views. This is X-rays and radio. This is just X-rays with different energies. So you see the stratification in energies. This has been suggested to be the remnant of SN 1181. Okay, this is a pulsar nebula 3C58. We'll get back to this one. So again, X-rays and radio. Another one, so maybe the remnant of SN 386. There's a pulsar in it. Maybe the remnant of SN 185. That's RCW86. Again, color composites. So you've seen just a few of them where we are certain and some more candidates. And I had essentially this list, like I've had this list for years. There's that many supernova observations, and you don't find that many new or young remnants. And so you don't expect this to change a lot, really. Okay. Well, this is just what happened. So there's a new one. Completely new object. This is about SN 1181. So we have Chinese records, we have Japanese records, and so it was somewhere here. So again, we don't know exactly, but probably within this circle. And so you may not recognize red asterisms, Chinese, or the green lunar log, but so you may recognize this W. Okay. And so the supernova is pretty clear, like it was actually a supernova, but finding the remnant has been more complicated. And so there's been a candidate, the one I showed, 3C58. And so I'm doing the story here about a bit of text because so it's been a bit controversial. So initially in the 80s, they just suggest that this remnant in the neighborhood could be the remnant. And then it wasn't until the 2000s that people could actually make measurements of like get estimates of the edge of how it's like expanding and things. And it doesn't match what you'd expect for 1,000-year-old remnant like this. So not consistent, not the remnant, not the remnant. If it were associated, like it's not. But it's controversial. So some people still believe it can be the remnant. And so this is Roland Cotes, so a Canadian astronomer. And while distances are notoriously difficult to estimate, and if you change the distance, well, you change the actual physical size, you change the energetics and things, and so you can you have room to adjust the parameters. And so if you change the distance, then yes, it can be a 1,000-year-old remnant, and it's possible. And that's a paper he actually wrote a chapter of a book on a handbook on supernovae, and he doesn't say it's possible. The title is the supernova of 1181 and its remnant 3C58. Assertive. But most people were thinking it's not a great candidate. So again, we're talking about we are talking about this one. Yes. Then something new happened. Something that was led by amateur astronomers. People who call them deep sky hunters. And what are they hunting? Well, not remnants, but planetary nebulae. Well, they look similar, like bubbles. And so they're looking at WISE data, that's infrared satellites. And there's tons of data, tons of things to look at, and professionals actually may not have looked at everything. And so the amateurs may have a role to play. And so they look at the data and they find bubbles and they find candidates of possible planetary nebula or other things. We don't know. Okay, and so in 2013, Dana Patrick found this. So these are 4 bands of WISE, and there's clearly something. There's something spherical. Maybe a planetary nebula. It's presented, so that's 2014 poster with many others. So it's unclear what it is, maybe candidate nebula. And then they work with professionals who follow up on this kind of observations. Like, so there's Parker at Hong Kong University, who was a group doing studies of planetary nebulae. But this one was not investigated for some reason. But the amateur astronomers looked again, these 3 people, and in 2016 didn't find anything so interesting. So it could have stopped here. The story could end in 2016. But then they looked again. So Pascal Levue, maybe the name is familiar, I think a bit famous. And he looked again and he found an unusual spectrum in the optical, and he went back to the professional astronomer who was like, okay, we're going to have a closer look. And so in 2018, it is said that they are setting up a team to really look at this new object. And that's a story as it's told mostly on this website, so you can read details. Meanwhile, in Russia, Professor Varanadze has also been looking for such bubbles in WISE data. And so in 2019, he's publishing this paper with the team about this object that they call it WS35. It's the same. Okay. So they have their own catalog, it seems. So they refer to a paper, so WS is WISE shell. And the paper they refer to from 2012, I think, actually only has 2, WS1 and 2. So I guess they expanded the list by then, but I've not seen the actual catalog. In the follow-up paper, they actually dropped this name. They no longer use it. Instead, they use this RASC name, which does exist already, but which is just for the central star. But this what's new is a nebula, so it's a bit confusing. Some confusion around the name here. And so what they find is interesting. So from the modeling of the star, so there's a star in the middle and there's a nebula. And looking at the spectrum, optical and X-ray spectrum of the star and the nebula, they find that the properties of the star and the nebula match what you'd expect for a white dwarf collision. So something quite unusual and something that makes a supernova. And so the star is super hot, active with a very fast wind, and you have this little nebula around it. And so if this was made from a supernova explosion, then this is a supernova remnant, like a new one. But so they find also that it's a young one. They estimate from the velocity that it's probably 1,000 years old. So that's 1,000 years old. We have records, so well, they assume that probably we missed it. Okay. Remind me where it's located again? We are back to the other team. This is the Ritter paper 2021 with Parker, with the Levue, okay, and others. And they study it again, and they find they come to the same conclusion regarding the physics, that this was a supernova, a weak type of supernova that we call type 1X, if you want to detail zoology. And so they are, first they are adamant that it's PA30. They claim the name, the discovery first in 2013. Okay, and this name has been used since. And they call the star Parker star after Parker. Okay, and critically, so it's a paper where the connection is made explicitly with the supernova. So the location matches, the properties actually match nicely. That's instantly it becomes the best candidate. And so they agree, as I said, that it's a white dwarf, a merger. But so the modeling differs in the details. So like this one think that so two white dwarfs collided and something remained that it's that is heavy enough that it will explode again. But these ones conclude that no, actually something remains. So there is what you'd call a zombie white dwarf, but it's not heavy enough that it will explode again. But everyone agrees that there has been that's a result of a white dwarf collision. And so there was a release I can show quickly, just flash this. So this is from 2021. And I just want you to see this. This is straight from the paper. This is a press release, but it has like axes and labels and contours and stuff. Maybe not ideal, but so that's what they had at the time. Oh, I'm too fast. Should mention, this is the white again, this is X-ray again. They have an O3 image and they have an S2 spectrum. They do not get an S2 image. What would it look like? Do you see some kind of structure here, maybe? No, three. This is what you get in S2. Okay. And so we have never seen a supernova remnant like this. We have seen some objects like this, maybe, like some planetary nebula, actually, and some nova, but not a remnant. And so this is his 2023, and he used the telescope so like, I think it's like a 2.4 meters or something like this. So like here at MDM Observatory, Kitt Peaks. So it's like big, but not that big. It just long exposure reveals the filaments. So unlike any other SNR. And so it may be because it's dominated not by the ejecta, but by the thing at the center, this very active star with hundreds of degrees temperature, with super fast wind. Maybe this is what is sculpting this remnant. What do you hypothesizing? And let me just show you the release that comes with it, because there's a slightly different view in colors. It looks like it pops more, yes, but it's the same. The same, just color mapped. Okay. And just to finish on this, really making the case for the association. So there is a Schaeffer 2023 wrote a review, like a really comprehensive review, like dozens of pages, reviewing all the evidence. And so first he starts by recapping all the indication that 3C58 was not the remnant, like independently of that, never was a very good candidate, this one. And then he argued for PA30 as a remnant. And it goes in steps, you have to be careful. So first, there's the fact that in 1181 there was a supernova. There is the fact that what we see this nebula, that's a supernova remnant. And then the fact that the remnant is the remnant of this particular supernova. And then by studying the nebula, you can say something about the explosion physics of this supernova. Okay. So you have to be to go step by step, and so he's making the case, and I think everyone, I don't know how Roland Cotes feels about this, but I think everyone now pretty much agree that this is a remnant. That PA30 is the remnant of SN1181. Certainly it's the better candidate now. And okay, just to finish on this, at the time it was submitted in 2023 by Ko et al. So I know this one was Chinese student was affiliated with my lab in Japan. And so I knew about the story a bit, but this is really when he started to work on it and report on it that I got really into it. And so this is XMM again, and it's showing Chandra data also. So actually Oskinova, she asked for Chandra observations that she got, but apparently were not used. So I think they were first published, but they become public after some point, and so they were used in Ko et al.'s paper. And Chandra just sees the central source. Yeah, I'll show that better after. But so I'm getting I'm getting really interested. So I first hear about this like sometimes in 2022, and so then presentations by Ko in spring 2023, and so I'm looking at all these images, and so I made this like I actually I did cut these images from the figures and put them in a presentation on slides and just align them so that I can see them all and try to figure out what are these things and how they match. And I'm just staring at these things and I'm like, what is this first? And like, there's all this stuff and I'm like, we have to do something better. So do we have short on time, but what do we have again? Quickly, this is WISE infrared. This is WISE again, same wavelengths but different stretch because there's such a high dynamic range that it's difficult to see everything at the same time. Then you get WISE again with a stretch so that you see the the outer part. Again, a stretch for the inner part. This is another WISE band, which shows the same, but you see it less. And then again, and then H alpha, that's new, but there's nothing. That's WISE again. We're getting into color images, how it's made. This is an RGB composite. So you put data layers in RGB. Okay, but you need 3 of them. There's 2 bands where it shows what to do. Okay, well, we can do 22, 22, and 12. Or maybe we can do 22, 11, 11. Well, that's not my 11 yet, 12 is same. But see, like ABB or AAB, or you can do other variants, but okay. And then if you want to show more, maybe, okay, this is infrared, and UV, 3 bands, plus contours for X-rays. So now we're getting a bit more crowded. The O3 image, the S2 famous one. Okay, if you like it white on black, you want it black on white, okay. If you want colors, we can do that too. That's the same again. So this is just color mapped, okay. You have intensity values that are color mapped to colors going from black to blue to greenish, yellow, white, okay? But so it looks better, maybe, I don't know, but the information is the same. It's the same image, same data. And, okay, this is X-rays. It's too smooth, too blurred. Where's my mouse? And this is X-rays again. This is too noisy, not enough smoothing. And this is then the Chandra one, just not a dot, almost a dot in the center. Okay. So you have all these images, and so I was thinking, if this is what we think it is, so the remnant, a new historical remnant, it should get an image just like the others, like something like these images. at least something like this, right? Like in these objects. Okay. And making so what we want is an image, a composite image made of all of this wavelength data that combines them in a way that is both pleasing to the eye and that conveys some information about the object, that captures the most salient features, right? It's not easy to do. And so that's maybe why it was not done before. But so as it happens, we do have an expert in image making on campus. Okay, so in English. And so I approached her, that was spring last year, I guess. Yes. So I approached the J in English. And I pitched this object. I was like, this is really important. We have all these images, we should do something about it. And she was not so moved.
Only like, you know, I don't know, 100, 200 pixels across, you know, like it's really horrible resolution. And then all of those nice, beautiful striations, they're buried in the noise. I'm going like, oh, I don't want to fight with that. I don't.
Yeah, you didn't feel like putting too much time and effort.
That's right. That's right. It would take a long time. And I went, this is way too much work for me, but I train you. So I said, you do the work. And he did.
So if you want to learn about how these images of deep space objects are made, check the website at the bottom. You can check the papers, like there is your review. There is what's the paper before that?
The techniques of astronomy.
The one in Alaska, what's the name? Rector. The Rector paper, you can check. You can check our portfolio, you can check our workshops, YouTube videos. And so I'm just going to summarize what it takes to make an image of this kind, like the kind of images I've shown before. So first, you have to get the data, obviously. So again, we use the infrared from WISE, X-rays, XMM, and Chandra. I got UV from Galex, but I didn't use it because it's a bit redundant with Chandra. Optical, so this S2 for the filaments, must. Also, I use pan stars to get the stars. We want the starry field so that it's like a space. And nothing in radio. Did I say that already? I don't know. So that's very bizarre, but nothing. And so everything was retrieved from public archives. That's good, except the S2 image is directly from FISM, so thank you. And the X-ray data, so needed some more processing. And so we put a student from here on this, so called Frederick, doing his PhD with Martha Fiab co-supervising. And so he did quickly the processing for XMM and Chandra data, but we get something better with everything that was available at this time. Then you get FITS files. So maybe you know about FITS files. So it's supposedly a standard. So I won't get into all the troubles you get with FITS files with headers that don't match or extensions that are not understood by the visualization software or like that it looks posterized and you have to rescale or whatever. Okay. Eventually you make it work. And you have to regrid them, okay, so that they all match and have the same frame with the same pixels. And then you can start making the image. The first step, so if you know anything about image making, so it's about not making color image, you work in grayscale and you do what we call stretch the histogram. So you adjust like the level so that it looks good, so that you see details. And so that means setting the min and max in your histogram, like the range of data values that's useful. Usually you have to apply some scaling to your data. So usually linear doesn't show anything. So commonly you have to use a log scale so that you can see the fine details. And you can play a bit more, like you can adjust the contrast and where you put the contrast of the bias. And so you do that, you play with this, you record this, and there may be different stretches actually that work for the same data layer and your many data layers. And so eventually you have a set of grayscale images that show details, okay? And then you have to make the image. And so the previous step, so the initial step, this is just a Python package, and just this Python package for manipulating fixed files. This is Carta standalone software for looking at fixed files. And the last step is done with like a image processing software. So this is GIMP, could be Photoshop, this kind of software. And so what you do, you take your grayscale images, you colorize them, and you blend them. Okay, and you can have any number of layers in principle. You just have find a way to like superimpose them, so that they can you see them all in a way that's balanced nicely. And so to do this, so all these adjustments, so I just want to say the tools used. So it's things like levels, so like again the min-max, or you match, or you map input to output, like curves, or that's similar idea. Inverting the image, thresholding the image. You can do things like sharpen and blur. And of course, you have to set the color, so adjust the hue and saturation. In the end, maybe crop or rotate, I don't know. But nothing like, like people with this software, it's like we paint, right? So nothing like that. That's irrelevant. Anything that's like brush or bucket or eraser, I don't know, that's irrelevant to what I'm talking about. This is these images are not painted. I colorize them and assemble them in a way that I hope looks good. So maybe it does. Okay. And so this is a screenshot of GIMP. And this is not the first try. Okay, this is the layers hierarchy. And this is a clean one. So I did it in 2 passes at least. And the first one full res with many tests. And then I started again from scratch at 4 times the resolution, knowing what I wanted, what works or not, and doing further adjustments. And at the very end, I cleaned it so that it's just what works. And so, yeah, so I have this gigantic 1 gigabyte file that I'm scared to reopen now. But so this is how it goes. Like you see how you have different adjustments. Each step is a new modification to some stretch or something, and then eventually colorized. You get masks so that sparks can shine through, and everything is combined in layers that are blended. So typically with screen mode, but so this is how you make a single image. Okay. So if you look, you can look by wavelengths. And so this is infrared, this is optical, this is X-ray, this is the full thing. So I just want to say, this is not an RGB composite. I did not use 3 bands and put them in R and G and B. Okay, this is not a red channel. This is pink, and so there's blue in it. This is not a green channel. There's white in this image. This is not a blue channel. Cyan has green in it. So it's not just RGB. It's like you colorize however you want it, and you blend the layers, any number of layers. And so just take a minute or 2 to explain 2 things. So for the infrared, I used only 1 band in the end that shows most of the nebula, but 2 stretches for the same band. Okay, and so in the middle, the interior, the stretch for the inner part, it's used as a mask for the outer one, so that the inner part shows inside. It's like doing HDR in a way, if you want. And I'm using deliberately the same similar hue, so that you get the correct message that it's the same thing, but a slightly different one, so that you can see clearly the 2 aspects. Okay, and so for the coloring, I'm doing nothing fancy here. This is a chromatic ordering. You see this, like infrared in red. At the other end, I'm using bluish tones for X-rays, and in the middle, green, it could have been yellow. And so the yeah, the X-rays maybe. So blue, okay. This shows nicely the complementarity, by the way, between the Chandras and XMM instruments. So XMM is more sensitive, it sees the diffuse emission, Chandra sees nothing. But Chandra has better resolution, so it was able to pinpoint the central source. And so I colorized it in a way that I wanted to like be sharp, like needle in the middle. And the filaments, so that's the main part, and that was a bit tricky. So here they look very green, but so when you blend the blue and red, you'll get purple, right? And so green on purple will look good, complementary colors. But you have to be careful, like if it's too much, it may be too much of a contrast actually. So I tried many different strategies with the filaments. So again, it's like going back and forth and back and forth. You are satisfied mostly. And so I did use some sharpening also. And the stars, in principle, you have 3 bands or more with the stars. So you could redo RGB just for the stars, but the data didn't look good. And so I ended up just using 1 band and just putting the stars white. It's good enough, I think, when you blend them, just looks like they're still white and they look like a starry field. And I try to adjust them again. It's difficult. You see, like they are, like they're big. They're like so that's instrument limitation, and I try to correct for this. And then at some point, I thought it was looking better, and then I look again, and I see like there's like an eyeliner on each star, and like no. Okay, so I ended up like with this. And so again, the image was not made in 3 steps like this. Okay, I'm just showing by wavelengths, but so really I did it. I did the infrared nebula, then I did the X-ray one, and then the filaments, and I think the stars and the central source in the end. Just that when you have it, then it's trivial to select whichever layers you want. And so this is infrared, this is optical, this is X-rays. But so really it was made in such a way that the full thing looks balanced, that you can see different things, and so you see how the infrared and the X-ray nebula overlap, but not exactly. And you see here it's more pink. So this is the inner bright infrared ring that shines through. You see here it's more bluish, purple, because indeed there is an X-ray nebula in the center. XMM sees it. You still get the central source, that's Chandra, and the filaments overlaid. So again, I had to adjust them so that if they're too strong, it looks like they're pasted on top. If they're too blended, it's like everything is mixed up. So it was a bit tricky to adjust it as JM had anticipated. But so in the end, we came up with something under guidance that we were happy with. Okay. Now I have an image and I have limited time left, but so what to do with this? So the point was to have an image that people can use, right? That people can use and see. And so how to get it disseminated. And so I approached people at HISA and at NASA so that they put them in their galleries. So they're good at this, they're good at public outreach, they have a nice galleries with images. And so I asked them and they accepted to add them. So what's new here is not the story has been told before. The story I told before, it's not mine, I didn't do any of the discovery, right? What I made really is an image. And so this is an image release. And so it was coordinated jointly between HISA and NASA in March this year. And so this is, they write a story based on what you tell them, and they put them on their website. And the Chandra is nice because there's like details and different wavelengths also. And so and the U of M also did a press release, and so it started to attract some attention, at least locally. And so I got, this page is actually because of the CTV interview. So that's not the one I like the best because it's like the news. So it's like 2 seconds. You're on, you're talking to a black screen. But then I also got something with Radio Canada. They came at my place and we had a discussion, and I went to the studio for CBC Radio also. And so, yeah, that's were nice experiences. And then we were like, okay, let's go for Apollo, APOD. And so it was accepted by editor Rob Nemiroff. So you know this every day, an image. I don't know how they do this, like it's crazy. Every day it's a good one with everything correct, nice image, caption, everything. So the text, we are credited for the text. So we provided some things, they rework the text so that it looks like it reads as an APOD text. And do you notice something different? The framing maybe? It's vertical. Yeah. So they cropped it so that it looks good on your smartphone. Yes. Yeah, we can scroll. Yeah. That's really, yeah. Okay, and yeah, we'll let you read the text after. So I hope it makes sense now. And I just want to show. So my point is we needed a better image. I mean, this is nice, but we needed an image that combines different data we have. And so before, at the time of this release, we got something like this. The story made it to Forbes. No, not bad. What do they use for illustration? Some random sketch, why not? And the Crab Nebula. And then you get the figure somewhere. So like this thing, you don't know, you scroll, you don't even know if that's a figure or an ad or something, right? And they don't want this, right? Ars Technica, that's a good one also, I think. Yeah, Crab Nebula. It's a newly identified remnant, not just any remnant, but they illustrate it with something else because they don't want to show this. This is just like not for the public, right? So after I made the composite image, we get this. So this is CNN. Okay. So they use this one. And this is happy with this one also. Starts with a bang by Ethan Siegel. So that's maybe one of the best blogs for astronomy. And so this is like the Monday visual thing. Not much text, but so it's visual based. So they need a good visual to start with. So now, again, the story, they could have run it like years ago. But so they needed an image that works better. Okay, and so I'm over time, so I guess it will be a good point to end the presentation. But yes, this is how I became like PR for Nebula. But really, I'm a physicist, so I'll squeeze some more physics in 1 more minute. So this is a new historical SNR, and this is a rare type of explosion. So this is a big deal for us. And so this is a unique opportunity to study such explosions, having this like undead star in the center of the nebula, a young one. And there's many, many questions to be answered about like this dust ring, the wind that's super powerful, what is powering it, and the filaments, of course, so we've never seen anything like this. And the structure of the remnant overall, like where is the shock, where is the shell, everything is unclear. And there are developments as we speak. So just this year, these are modeling efforts in 2024, 1D modeling, 2D modeling. This is the kind of stuff I do on the right. And so, yeah, this is typical at the bottom, but to get filaments, you will need something more. And new observations in radio, still nothing significant. And this is optical spectrography. And the filaments, that's interesting. Actually, it looks like they're coming from the center, but they are not attached at the center. Okay. Yeah, you cannot tell from this, right? It's in projection. So it's always like that in astronomy images. This is the best I could do, but it's 2D. It will be 2D. It is a far cry from knowing the 3D structure. And this is what I'm interested in, the 3D structure and evolution of supernova remnants. So I've not done any modeling on it myself. We have plans with CO this coming year, maybe. I don't know what time I will have to work on this. But for sure, there will be more coming, observations and modeling. And it started with amateur astronomers. And that's it. Thank you.
Yeah, we got some time for questions if you don't mind.
Yeah.
Any questions?
Do we know how big the amount of mass of the remnant? You say it's a zombie. How,
Yes.
give us an idea compared to other white dwarfs.
And so the mass of the remnant, I don't know if we know exactly. So what was the white dwarfs? So typically they are like around solar mass. The two collided, and the explosion was weak. And so what was ejected was like a fraction of a solar mass. And what remains, so I would have to check what's if there is agreement. But so I know initially people were arguing it may be above 1.4 solar masses, so still unstable, or it is below, like so now stable. But so yeah, which yeah, I don't know if I've converted this number, but so yeah, yes.
What causes the puffball look projectile?
Yeah.
Sorry, I missed the beginning.
What causes it to look like puffballs?
Like
The ejectile.
yeah, so you mean this?
No, the blue.
The blue? Oh. Well, I don't know if I can tell why actually. So yeah, there is some structure that you see here, and I'm not sure how to interpret it. So yeah, I see some, like I don't know how to describe them. And again, it's not very typical. Like typically you see like some fluffy structure from related instabilities, so that we understand. And so this one, I'm not sure exactly why, but no, it's faint also, like it's borderline detection. So maybe we are over trying, but yeah, there's nothing much that's like that.
I find it fascinating that you could go back into the Chinese literature and find it. I wonder if there's been much look at the Arabic literature.
Yeah, and so again, it's not me who did this part, but so yes, we do have records, and it depends what times really. So like 1,000 years ago, like 1006, 1181, it's mostly Asia, and so Japan, China, like civilizations, they rise and then it moves to another part of the world maybe, and probably just depends when they happen. And so we have for this one here, I don't know, but for this we have all sorts of records from different places all over the world, but not always all of them at the same time.
Thank you. Extraordinary work.
But yeah, again, I cannot take all the credit for this. What I did is the medicine over here.
Hi, I have a question. Just wondering if you can review for us the nuclear physics that actually works in a 1AX, like really from a layperson perspective.
Yeah.
My understanding is a white dwarf is oxygen and carbon. And so, if I remember correctly, I think we said there was a collision of two white dwarfs.
Mm-hmm.
So how does that generate additional energy, and then how does it not go to a neutron star or a black hole?
And so we're getting a bit technical. I think I will backtrack a little bit and talk in general about thermonuclear explosions before we get into 1AX, which is like a subtype. So the more we look, the more we see like subtypes, and we have to explain and come up with things. So for thermonuclear explosions, so the basics is it's a white dwarf. And one of the main, so a white dwarf has a stability limit in terms of mass. So if it grows too big, it will explode. And it may get some extra mass if it has a companion. And one of the main questions is what kind of companion? And so it may be a normal star. This is the white dwarf is called a degenerate object. It's sustained by degeneracy pressure of electrons. So this is a normal star. So this would be called the single degenerate star. But it may be two white dwarfs orbiting each other, and they may exchange matter, or they may even collide. And so this is two degenerate objects, what's called a double degenerate star. It's been decades that people have been arguing for one or the other. It's probably the box, actually. And this is just, okay, like an overview. Then how does it actually explode? And so there's different ways you can actually make the white dwarf explode. So typically, it's what I said, there's a stability limit, 1.4 solar masses. It reaches this limit, and there will be a detonation in the carbon center that destroys the white dwarf. That was the basic idea. But in fact, it needs not be like this. You can get subatomic mass of white dwarfs that explode with a more complicated mechanism, like an explosion on the outer layer that triggers another detonation in the center. And this applies to both scenarios. And so in this case, you may get a collision and deep direct detonation, or you may get a double detonation induced by mass transfer. And the other may survive, or may not. Then you can get a double detonation or things like this. And so there's a plethora of models now really, and this is what I'm using, so I don't do these simulations. People work just on this, on making stars explode. And I'm using their models as inputs for my simulations of the Raman phase. And so to get to your question, so the 1AX is a subluminous type of thermonuclear explosion. So it's less mass ejected, less energy. And we have some of these models that can explain this. And this one, most people are thinking this was a collision of white dwarf with a CO white dwarf and a neon oxygen one. And so the carbon detonated, but not the rest. And so you get an explosion, but something that remains. Or at least that's the main idea. Thank you.
How common are those S2 scopes that you see there, the filaments? How common are those in supernova randoms?
The filaments?
Yes.
So yeah, I will say it again. They are not. Where is it? This right now. This. And so I have never seen a remnant like this. Just never. Okay, we have so we have different shapes, okay. Like sometimes it's unclear, you get some filament. Typically a shell. When you get some fluffiness inside, so it's like this kind of like shredded stuff, or this is typical, like this fluffy structure. This is hydrodynamic instability, we understand. But something like radial filaments for a remnant, no, that's the first one. And so actually, we've seen things similar, but not supernova remnants. And so I told you this is not supernova remnant, it's different, but actually this one looks the same, the planetary nebula. And this is most probably because of the activity of the central source of the wind. Or photoionization. So it's because what the thing inside is very active. That it does this thing. This is a planetary nebula. This is a nova, not supernova, so much fainter. It's like just a burst. It doesn't destroy the thing. You can go nova again and again. And you see like it get a bit, not as long, right? But you get similar effects. So this is probably sculpted by wind or radiation. And so yeah, I can say it. Like, I wanted to say this. So, you know, when we have, like the crab, this is powered by the pulsar inside. Okay, and so we call it a pulsar wind nebula. And so this new object, it is quite possible that most of what we see is not made not, what you see maybe is not the ejecta per se and the collision with the ambient medium. Maybe it's mostly shaped by the activity of this central zombie star. And so maybe we can call this a white dwarf wind nebula, or we will. So I checked. I didn't see it on Google, so this is recorded, right? So then I can claim priority. But I don't know. We don't really understand the subject.
I just want to say, I want to emphasize how heroic Gilles' image is. He did an enormous amount of work. He really learned advanced techniques and he figured out with a conceptually engaging image. I just want to tell you how heroic that is.
Thank you for your Yes, it was not easy. I don't know how it looks, but it's work.
Any other questions?
Well done.
Well done. Thank you very much, Jill.
But I hope you liked it. I'm usually people like it, but I've seen like on APOD like forums. I remember someone was like, "Oh yeah, I'm not so good." But then they read the text and they were like, "Wow, that's the story is great." And that's the point, right? I want people to engage with it, and so I'm fine with it.
I'd just like to say thank you on behalf of the RASC.
Thank you very much.
You're most welcome. And that brings us to the end of our meeting. And again, as usual, we have a gathering over at Boston Pizza. So Jill, Jan, you're most welcome to join those that are going over. And we'll see you all later. So have a great night. Thank you.
That was awesome, Chris.
Yeah. So now you can say if you like it or not. No, you can.
Yes, it was awesome. 110%. But you got the bonus points on that one. Yes, we can. Actually, that's a good idea. There you go.
Question?